Dynamic programming bottom-up versus top-down. Mastering optimization techniques in algorithm design. Dynamic programming, DP, stands as a cornerstone of algorithm design, enabling efficient solutions to complex problems through clever reuse of computed results. At its heart lies the art of breaking down problems into smaller subproblems and storing intermediate outcomes to prevent redundant computations. This article delves deep into the critical distinction between bottom-up and top-down dynamic programming, equipping you with the insight to choose the optimal approach for any given challenge. The choice between iterative bottom-up and recursive top-down techniques often determines whether your solution scales efficiently or falters under computational pressure. By understanding their mechanics, trade-offs, and implementation nuances, you'll unlock powerful tools for tackling classic and modern algorithmic puzzles alike. What is dynamic programming? Dynamic programming is a paradigm that solves optimization problems by decomposing them into overlapping subproblems and caching intermediate results. Unlike greedy algorithms or divide-and-conquer approaches, DP prioritizes reusing previously solved instances to reduce time complexity dramatically. The core principles of dynamic programming revolve around identifying optimal substructure and overlapping subproblems. Optimal substructure means a problem's optimal solution relies on solutions to smaller instances of itself. Overlapping subproblems occur when identical subproblems arise repeatedly during computation. Classic examples include the Fibonacci sequence, shortest path finding in graphs, and resource allocation problems. For instance, calculating the nth Fibonacci number naively leads to exponential time complexity due to repeated calculations, whereas DP reduces this to linear time via memoization or tabulation. To implement DP effectively, programmers must define a recurrence relation, a formula expressing the problem in terms of smaller subproblems, and decide whether to store results iteratively, bottom-up, or recursively, top-down. Both methods share the goal of eliminating redundancy but differ sharply in execution strategy. Bottom-up dynamic programming. Iterative mastery. Bottom-up dynamic programming starts with the simplest subproblem and progressively builds toward the final answer. It employs iteration instead of recursion, often leveraging arrays or tables to store intermediate values systematically. This approach eliminates the overhead associated with recursion stacks and function calls, making it ideal for problems requiring strict performance guarantees. However, it demands careful planning of the order in which subproblems are solved to ensure dependencies are resolved correctly. Memoization-free. Bottom-up DP does not rely on recursive calls or cache lookups, making it simpler to debug and optimize for speed. Space efficiency ***. While it may require significant storage for large grids or sequences, space can often be optimized using sliding windows or single-dimensional arrays. Deterministic execution ***. Since it follows a fixed loop structure, it avoids unpredictable behavior caused by excessive recursion depths or stack overflows. A prime example is the Fibonacci problem, implemented with bottom-up DP using a loop. Starting with base cases fib 0 equals 0 and fib 1 equals 1, we iterate up to n, computing each subsequent value from stored predecessors. This yields O, n, time and O, 1, space with optimization techniques. For the knapsack problem, bottom-up DP constructs a table where rows represent items and columns represent capacities. Filling the grid step by step allows us to compute maximum values without revisiting earlier computations, demonstrating the elegance of structured iteration. Top-down dynamic programming. Recursive intuition. Top-down dynamic programming begins with the full problem and uses recursion to break it into smaller subproblems. A key component is memoization, a technique that stores already computed results to avoid redundant work. In contrast to bottom-up methods, top-down approaches are closer to intuitive problem-solving. Programmers write recursive functions that solve each subproblem once, then save the result for future reference. This makes debugging and visualizing the process easier for beginners. However, top-down DP introduces overhead from managing function calls and maintaining a lookup table, often implemented as dictionaries. Additionally, improper handling can lead to stack overflow errors for deeply nested recursions. The Fibonacci sequence serves as another illustrative case. Using top-down DP with memoization, we begin with fib_n, check if the result exists in our cache, and if not, compute it by recursively calling fib_n1 and fib_n2. Memoization ensures that each subproblem is solved only once, achieving O(n) time complexity. Consider the longest common subsequence, LCS, problem, where top-down DP explores possible subsequences by comparing characters at different positions. The recursion tree branches exponentially without memoization, but memoization prunes redundant paths, improving efficiency significantly. Choosing between bottom-up and top-down approaches, selecting the right approach depends on factors like problem size, input constraints, and individual preferences. Bottom-up is generally better suited for flat memory structures or when exact control over computation flow is needed. Top-down offers clarity in logic but may sacrifice performance in extreme scenarios. For small inputs, the difference in runtime between bottom-up and top-down methods is negligible. However, as input sizes grow, the overhead of recursive calls and cache management becomes harder to ignore. In competitive programming, bottom-up solutions are sometimes preferred for tight time limits. Memory considerations: both methods require memory for storing intermediate states. Bottom-up DP often pre-allocates space upfront, while top-down methods dynamically expand the cache. For memory-limited environments, bottom-up techniques allow more precise optimization, such as discarding unnecessary data once processed. Space complexity varies depending on the problem. For example, bottom-up Fibonacci requires only O(1) auxiliary space when optimized to retain only the last two computed values. In contrast, a top-down version with memoization typically uses O(n) memory, even with constant space optimizations. Advanced concepts, state compression and space optimization. Efficient dynamic programming often involves minimizing space usage without sacrificing correctness. Many bottom-up implementations replace multidimensional tables with single-variable updates or rolling arrays to cut memory consumption. A notable example is the edit distance problem, traditionally solved with a 2D array of size mxn, where m and n are string lengths. By observing that each row depends solely on the previous row, we can compress the solution into a one-row array, reducing space complexity to O(n). Similarly, the climbing stairs problem demonstrates how space can be minimized further. Instead of storing the entire history of steps taken, we track only the latest two values required to compute. These optimizations hinge on recognizing dependencies within the problem domain. For instance, if a current state relies only on prior values, not diagonals or arbitrary distances, significant space savings become achievable through strategic redesigns. Pitfalls and best practices in implementing DP solutions. Newcomers often struggle with formulating accurate recurrence relations or misidentifying overlapping subproblems. Thoroughly analyzing the problem statement and working through manual examples helps expose hidden patterns. One common pitfall occurs when assuming a naive recursive approach suffices without adding memoization. This can lead to catastrophic inefficiencies, as demonstrated by a standard factorial function that fails to leverage cached results despite having obvious overlapping substructures. Always validate your DP formulation by testing edge cases. For example, when building a bottom-up Fibonacci calculator, verifying that it handles n equals 0, n equals 1, and negative numbers appropriately prevents runtime errors later in development. Debugging DP programs benefits immensely from logging or printing intermediate values. Observing how the solution unfolds step by step clarifies why a particular configuration might yield unexpected outputs, especially in complex multidimensional problems. Real-world applications beyond textbook examples. While classical problems like the knapsack and LCS are staple learning material, dynamic programming shines brightest in applications requiring vast-scale optimizations. One prominent area is bioinformatics, particularly DNA alignment and protein folding predictions, where massive datasets necessitate efficient computation techniques. In finance, portfolio optimization models frequently employ DP to balance risk and return across diverse assets. Algorithms calculate optimal investment allocations based on historical returns, market volatility, and investor objectives, all handled elegantly by well-structured DP formulations. Video game AI also leverages DP extensively. Pathfinding systems determine the most efficient routes for NPCs by evaluating hundreds of potential moves per second. These decisions are influenced heavily by grid layouts, obstacle placements, and other environmental variables modeled through DP mechanisms. Emerging technologies like quantum computing and artificial neural networks face challenges similar to those addressed by DP. Researchers apply DP principles in designing fault-tolerant quantum circuits or optimizing training processes in deep learning architectures, showcasing its versatility beyond conventional software domains. Evolving trends in dynamic programming research. Ongoing advancements continue pushing the boundaries of what dynamic programming can achieve. Recent studies explore hybrid approaches combining DP with machine learning for improved predictive analytics. These experiments suggest new ways to approximate optimal solutions faster than traditional methods alone. Quantum-inspired DP variants aim to handle NP-hard problems more gracefully by exploiting superposition properties. Though still experimental, preliminary findings indicate that such paradigms could revolutionize fields like cryptography and large-scale network routing. Parallel processing frameworks also integrate DP techniques to distribute workload evenly among distributed nodes. Cloud-based platforms utilize parallelized DP pipelines to accelerate tasks involving big data processing or real-time simulations requiring massive concurrency support. Educational resources now emphasize teaching not just individual DP patterns but broader conceptual frameworks adaptable across varying contexts. Interactive coding platforms provide instant feedback loops allowing learners to adjust their implementations dynamically, enhancing retention rates substantially compared to passive learning styles. Tools and resources to enhance your DP skills. Leveraging specialized tools enhances productivity while mastering dynamic programming fundamentals. Platforms like LeetCode offer curated lists of problems categorized explicitly for DP practice, complete with difficulty ratings and hints towards effective strategies. Integrated development environments, IDEs, equipped with automatic memoization generators simplify implementing top-down solutions without manually writing decorators or caches. Tools like Visual Studio Code and PyCharm increasingly incorporate intelligent suggestions that identify opportunities for refactoring inefficient code segments. Academic texts remain invaluable sources for deeper theoretical insights. Books such as Introduction to Algorithms, CLRS, provide rigorous mathematical analyses behind popular DP designs alongside exercises that reinforce comprehension. Online forums like Stack Overflow host vibrant discussions where practitioners exchange war stories and troubleshoot difficult edge cases encountered during coding. Interviews or hackathons. Engaging actively in these spaces accelerates growth exponentially relative to solitary study sessions alone. Conclusion: dynamic programming bridges theory and practice through elegant solutions grounded in mathematical foundations yet applied seamlessly in cutting-edge technologies today. Whether you're solving classic textbook problems or navigating sophisticated industrial applications, mastery of both bottom-up and top-down approaches grants unparalleled flexibility in crafting robust algorithms. Remember, no single method universally superior. Practice deliberately switching perspectives, implement top-down recursions when conceptual clarity matters most, transition smoothly to bottom-up iterations when performance becomes paramount. With consistent effort, you'll cultivate instincts essential for success in algorithmic problem-solving and beyond.